we have actually 3 speakers, and out of these 3, we have our own from IISER Kolkata. The first speaker belongs to actually IISER Kolkata, Subimal there. Subimal there started actually his research career from PRL, and then he worked in various institutes in various capacities, and for the last I would say that more than 1 year he is actually associated with us in IISER Kolkata as a research associate. And his talk today is going to speak on the variation of self-imaging length in multimode waveguides beyond the paraxial approximations. So I invite Dr. Subimal Dev to deliver his talk, and let's listen from him about this thing. So please.
Thank you for your nice introduction. I'll share my screen. I hope my screen is visible.
Yeah.
And I'll just roll on to the next slide to see if you can.
It's working. Yeah.
Okay.
Nice.
So I will. Today I'll begin my talk in the afternoon session. This is not much to do with the quantum optics formulation that we have been having in all the talks so far. This is rather about improving the efficiency of optical circuits, and for that we will take a look at 2 simple geometries of waveguides. One is a step index slab and another is a graded index slab, and we will look at them in the paraxial and the non-paraxial regime. Now, why is this important? This is important because the optical circuits that will eventually be used in for designing quantum computers or in any of the nanophotonic circuits that would be used, they would consist of small optical elements which are interlinked. And when you link elements together, it is very important that that light from one element is efficiently coupled into the next element. If that doesn't happen and you have a loss at one of the interconnects, and such cascading losses keep on occurring over all the interconnections, then it would ultimately lead to a very lossy circuit. And moreover, with miniaturized optical components, one would like to go to sources which are very small in size, and that leads us to the non-paraxial domain. And to introduce, I would begin by giving a small introduction about self-imaging, which is one of the novel optical phenomena that is getting a lot of attention recently. It was of interest for quite some time, but recently it has picked up a lot of interest in various fields, and that also is very useful in enhancing the efficiency of optical circuits. That we will be using when we discuss the step index slab. And after that, I would discuss the results we have for the step index slab, and then move on to the results of the graded index slab, a parabolic index slab, where we will look at self-focusing rather than self-imaging. So let us start with self-imaging. Self-imaging was a phenomenon that was observed more than a century ago, in 1836, by Henry Fox Salvo. And he did that, and he observed it when he was looking at the images behind a grating that was illuminated by a plane wave. He observed that one can find the image of the grating being repeated at regular intervals, and that observation led to the phenomenon that we now call as self-imaging, or the Salvo effect. Both these terms are used synonymously, and over time they have been this effect has been studied in a lot of different kinds of optical elements, which includes gratings, waveguides, different kinds of metal dielectric setups where you can excite surface plasmons, and even in hybrid optical circuits, hybrid or all optical integrated circuits, by which I mean you have semiconductor devices and optical fibers all linked together to deliver the signal from one end to the other. Now, after 1836, in 1881, Lord Rayleigh, he quantified Talbot's observation. He quantified Talbot's observation and he gave an expression for the distance at which the self-imaging occurs. And that distance is called the Talbot distance. And the expression I have already given over here, this is an expression that we will take into account when we look at the results for the step index slab. But just to note the fact that in the paraxial approximation, that is when the dimensions of the system, that is A, is much, much larger than the wavelength being used, the Talbot distance reduces to 2a square over lambda. So this, to be a little more specific about the Talbot effect, you have an incoming field of light, which you can quantify by the electric field. The input field profile, it falls on an element, which could be a grating, as I have specified by the dark blue line. It propagates, and it can propagate through free space, or you can make the input profile simply propagate through a waveguiding channel. The waveguiding channel also could be of two different kinds. One that has got translational symmetry, that is, it's simply a wave. It is just something like a slab or a optical fiber, which is in which there is no change in the structure along the direction of propagation, or there could be some periodic elements that are introduced along Z. So you can even in all these cases, one observes the output field at a certain distance, the output field to be repeated at a certain distance L or multiples of L. And the output field is replicated, is a replica of the input field up to a phase factor phi. And this happens at all multiples of L. And we will be concentrating on the case for a waveguide channel, a one-dimensional waveguide channel, which has got translational symmetry. That is, there's no change in the structure of the waveguide along the direction of propagation. Now, here is a pictorial representation of the Salvo effect, which is well known to a lot of people in the audience, I presume. But for the sake of completeness, I would still present the results that are important for the rest of the talk. So I have a waveguide. The walls and the spacing between the walls of the waveguide is 2a. The direction of propagation is Z. And the transverse direction, the direction that's transverse to the waveguide axis, I denote by X. A field is injected into the waveguide at this point. And as the field propagates, if it is a multi-mode waveguide, that is, the waveguide supports more than one mode, as the field propagates, each mode acquires a different phase. And as the individual modes propagate, they will interfere and they produce a very nice interference effect along the length of the waveguide. And at the Talbot distance L, you will see a replica of this input field. But let me tell you that it will be produced at multiples of L only if the input field is symmetric. So if the input field is symmetric, the replica at this distance L, which is 4a square over lambda, if the waveguide width is 2a, it will be reproduced faithfully up to a phase factor, overall phase factor of minus pi by 4. If you have an antisymmetric field, it is easy to work out the calculations. I would refer to the works of Professor Michael Berry, and he has got a very detailed calculation of self-imaging taking place in waveguides. These kind of calculations, and you would see that for an antisymmetric field, the replication takes place at a distance 2L. And if you have a general field which could be shifted away from the center, so you cannot classify it as being symmetric or antisymmetric, in that case, it will be replicated at a distance of 8L. And the overall phase factor in the case of the general field and the antisymmetric field is 0. It's only for the symmetric field that you are going to acquire a phase factor of minus pi by 4. And for a waveguide, let's say with metallic walls where the field does not penetrate into the walls of the waveguide, you can represent the electric field as sine and cosine functions of x, sinusoidal functions of x within the walls of the wave, or rather in between the walls of the waveguide. And this factor of 1 by root a comes up for normalization of the individual modes. Outside the cavity that is within the walls of the waveguide, if we assume that the field is 0 for a metallic waveguide, in that case, for the paraxial approximation, one can find that the propagation constant is proportional to m squared. Propagation constant for the mth mode is proportional to m squared. And this m squared dependence brings in this beautiful carpet that you see over here. And what we are going to look at is something beyond the paraxial approximation, where the lambda could be of the order of a. If lambda is much smaller than a, this relation holds good. If not, then the paraxial approximation fails. In other words, when I look at the paraxial approximation, I mean that you have the width of this input beam being very small, and as it propagates, it is going to spread out very fast. If it would be propagation in free space, so you can have a beam that is very thin. In that case, it's going to diverge a lot, and that would be the non-paraxial regime. And we will be looking at the non-paraxial regime of propagation for a Gaussian input beam. That is, the input beam profile looks like a Gaussian. Of course, there are a few more assumptions that we have made, and I'll talk about that very soon. So here is a geometry of the waveguide, the slab waveguide that we are considering. You have the core material sandwiched between two dielectric layers of lower refractive index. Usually, for a slab waveguide, you'll put the core on a substrate, and on top of the core, you'll have the cladding. If it is a symmetric waveguide, then the cladding and the substrate would be made of the same material and would therefore have the same refractive index. So the refractive index on either side of the core, if it is symmetric, you call it this step index symmetric waveguide. And that is what we are going to consider for our first part of the presentation. In such a waveguide, you have a lot of different modes that get excited, but out of them, we will be concerned only with two of the different kinds of modes. Primarily, the guided mode, which remains confined only to the core of the waveguide, and the radiation modes, which leak out of the core into the cladding, and thereby we lose energy of the input beam as it propagates through the waveguide. The other thing that we must note is that the waveguides we are considering are thin and multimode because the width of the input beam is very small. So let us quickly look at or review the self-imaging mechanism that that we have, or that is going to take place in the waveguide. You have the Gaussian beam that will be injected from the left end into the waveguide. The Gaussian beam would be characterized by a quantity W0, that's a measure of the width of the waveguide, width of the beam. As it propagates, the individual modes, they travel along the length of the waveguide, interfere, produce the interference pattern, and at a distance d, you will get the first self-image. Remember that this first self-image is a faithful replica of the input only up to a phase factor of -π/4. So this multimode interference effect is something that that creates this beautiful carpet, and at this end, at the distance d from the input, where you have the first self-image being formed, that would be a very nice place to truncate the waveguide and let the next optical element connect into or collect this light, because almost the entire beam is very nicely localized over here. So you would have less losses, and the assumption that we are making, I told you that we also have a small assumption that we are making. The assumption that we are making is the Gaussian beam is being fed at its waist, which means that the wavefront of the Gaussian beam at the input is perpendicular to this, or rather parallel to the axis of the waveguide at the injection point. So that is the assumption we go ahead with, and having spoken to some of the experimental people, I've been told that it is possible to do that. So I believe it's a reasonable assumption. So the symmetrically fed input produces multimode interference, and we get self-imaging, which would be a nice point to truncate the waveguide to produce the or to connect the next optical element. And just to remind you that this multimode, this case of propagation of waves in a waveguide, whether it be the slab waveguide or a step index waveguide or a graded index waveguide, it is the same mechanism that that we would be looking into. So the first case of the step index slab is what I'll be talking about next, followed by the graded index slab. And the graded index slab is a problem that is a work in progress. I call it a work in progress because it has just been submitted. And the step index, the results of the step index slab have recently been published. So starting with the step index slab, what is the problem statement? If I repeat the problem statement once, the width of this input beam is a parameter that we will vary, and we want to see what happens to the self-imaging distance. Does the self-imaging distance B increase or decrease, or how does it increase or decrease, if at all, with the width of the input? That is what we would take a look at. And if you recollect that how the width of the input is related to the paraxiality of the beam, an increase in the width W0 of the input beam would mean that you have paraxial input, and a decrease in the width would mean that you have a non-paraxial input. Well, of course, there are certain ranges of W0 that would qualify this beam to be called a paraxial or a non-paraxial beam. And we look at the work of Nemetto that was published in 1990 on non-paraxial Gaussian beams, where he classifies, or where he rather demarcates the boundaries of when you call a Gaussian beam paraxial and when you call it non-paraxial. So K is the wave number for the beam that is being used. So if K times W0 is 4√2 or more, you would call it a paraxial beam. Anything between 2√2 and 4√2 is good enough for describing this Gaussian beam with a first order approximation term. With KW0 lying between √2 and 2√2, you require at least one more term. You require rather one more term, or rather two terms, to describe the beam properly, and therefore the first order approximation starts breaking down. When you require more terms to describe the Gaussian, you have entered the completely non-paraxial regime. And when that happens, in fact, once you have gone out of the paraxial regime towards the non-paraxial regime, the Gaussian beam loses its character of being called the quote-unquote Gaussian beam, because you have to describe it with extra terms. But nevertheless, describing it with this kind of a expression still holds. And we will see that a numerical study of the beam propagation in a slab waveguide actually matches this classification put up by Nemoto, who did it from with a completely different perspective. So the scheme that we are going to use is a finite difference scheme. This is a numerical scheme that we have used to analyze propagation in a waveguide, and this is not a very difficult scheme to understand. The scalar wave equation that guides this, that describes wave propagation in this one-dimensional system, is written down over here, and beta square, or the propagation, beta is the propagation constant for the modes of the waveguide. And for the finite difference scheme, this derivative, the second order derivative, is written as a finite difference. When you write it as a finite difference, you discretize the grid. That is, you try to find the solutions of this differential equation by looking at discrete points on your entire x-axis rather than a continuous set. So the second derivative is expressed in terms of the field values at the point x and the neighboring points that we have on the grid. So the second derivative at the point xi would be written in terms of e at xi, e at xi plus 1, and e at xi minus 1. So that would give us a second order accurate description of the second derivative. And if you plug those values into this transform differential equation, which you have transformed into a finite difference form, you'll get a set of equations. The number of equations being the number of grid points you have taken, and that would transform this differential equation into a linear algebraic equation, which is written in this form: M being a tri-diagonal matrix if you have used second order accurate formulation, and E are the eigenvectors or the eigenmodes of the system, and beta square are the eigenvalues, beta being the propagation constants. One can also go for a fourth order accurate scheme where you write the second derivative in terms of the field values at that point, that is EI, at the neighboring points, EI plus 1 and E minus 1, and the next nearest neighbors, EI minus 2 and EI plus 2. It is very easy to work out this expression for the second order derivative, and this will lead us to a pentadiagonal matrix for M. Now these you can solve for the propagation constants and the eigenmodes by diagonalizing the matrix M. But mind you that you will need specialized routines for for diagonalization. There are several routines which are available, but it is good to use routines which are specialized for these banded matrices. If you use routines which are most general, then you may not get a very accurate value of the propagation constants, that is the eigenvalues. So it is always good to use the routines which are specialized for banded matrices in this case. Now, having described the finite difference scheme, let us look at the two schemes that we have described for finite difference, the second and fourth order schemes. Now, if you compute the eigenvalues using the second order approximation and the fourth order approximation, the eigenvalues for the waveguide that we have considered, they do match for the higher values of beta, but there is a disagreement in the lower values of beta. Now, the higher values of beta would mean the beta corresponds to the tangential component of the wave vector. That is the component of the wave vector parallel to the interface of the waveguide walls. So a higher value of beta would mean a lower value of kx. That is a transverse component of the wave vector. And the lower the value of kx, the lower you go in your mode spectrum. So highest value of beta would correspond to the lowest mode. So the disagreement in both the schemes is in the higher values of kx, and that is expected because iterative schemes for finding eigenvalues, they become less and less accurate as you go for higher eigenvalues. And but nevertheless, we will see that we need not be concerned with this disagreement, because if you look at the different modes, the guided modes and the radiation modes which we are concerned with, they do fall in the region where both schemes agree. I'm just shifting the slides back and forth so that you can compare the region where both the schemes agree. So one can use the fourth or the second order scheme, whichever one is convenient with, but we have used the fourth order scheme throughout. So here I have for our waveguide, which is we have used a wavelength of 1.55 microns and a step index fiber with a core refractive index of 3.48 and a cladding refractive index of 1.44. These are standard values which I've picked up from literature. And I have taken a waveguide of width 31 microns. So that is about 20 times lambda. And you will find that you have a set of guided modes which are marked in blue and a set of radiation modes which are marked in red. The rest of the modes are the evanescent modes, and these modes, they will decay as they propagate along the waveguide length, and we need not be concerned with them at all at this point of time, because we will never get to excite that many modes. So let us move ahead. Now, this scheme that we have used has to be tested for its accuracy. So the first thing we did was we checked the reconstruction of the input. We have an analytical form of the input, which I have already shown you earlier. Let me just go back, quickly show you that expression, that is E0 e to the power minus x by W0 whole square. This is the input that we have fed in, and when we reconstruct it in terms of the eigen modes that we computed from the finite difference scheme, you find that the error or the difference between the analytical and the reconstructed scheme, the absolute error, is 1 in 10 to the power 13, and that is quite acceptable. Here also, the very standard integration routines will not work. You do need accurate or higher order integration schemes for computing these overlap integrals. Next comes the computation of these input coefficients. See, these overlap integrals, or CP, which we have computed over here, they will depend on the width of the input beam. As you change the width of the input beam, that is, you go from the paraxial to the non-paraxial domain, the number of modes that get excited increase. On this plot, on the rightmost end, you have the paraxial domain. As you move towards the left, that is lower values of W0, you will have you are going to the non-paraxial domain. So you'll have greater divergence of the beam and more modes being excited. So you can find plots of two different colors, one in red and a set of plots in green. The set of plots in red, they correspond to the guided modes of the waveguide, and the curves in green correspond to the radiation modes. There are 4 regions which I have marked over here, R1, R2, R3, and R4 on the graph. R4 corresponds to the region which is classified as the paraxial region by Nemoto. R3 corresponds to the region where the first order approximation holds. R2 corresponds to the region where the first order approximation starts failing, and R1 corresponds to the non-paraxial regime. So when you are in the non-paraxial regime, I have amplified this non-paraxial regime R1 on the plot on the left side. You find that the curves of the guided modes and the curves of the radiation modes, they are bunched together. We do not know have an analytical answer or analytical analysis. We haven't analyzed this part, and I'm not sure whether it can be done, because for the step index guide, one cannot have an analytical solution for the propagation constants. So we have to rely on the numerical results. There's one more point that I would like to say over here, is that the x-axis I have plotted not just W0, but rather W0 by WF. WF corresponds to the width of the fundamental mode. And that we have done to ensure that the width of the input that we are analyzing does not exceed the width of the fundamental mode. We will see a reason why that is often taken into account when we discuss the graded index slab. Now, apart from this, there are a few more interesting results when it comes to self-imaging, or rather the point where we want the next optical element to be connected. We look at the intensity at along the axis of the waveguide, and when I plot the intensity along the axis of the waveguide for W0 by WF is equal to 0.3, which corresponds to the paraxial region, you find that the carpet is nice, smooth, and you get a very nice replica of the input. And if I plot the intensity along x equal to 0, you find that the intensity is replicated. Well, these plots I have normalized with respect to the intensity at x equal to 0. So at the Talbot distance, we find that the intensity is faithfully reproduced for the paraxial regime. But when you go to the non-paraxial domain, that is W0 by WF is 0.04, which is well inside, you will find that you can hardly look at, or you can hardly find the intensity pattern. I'm not sure whether you can make out that the intensity carpet exists, and but nevertheless, I'll try and expand this so that you can see that indeed you have a carpet. But there is one more thing to observe. What you observe here is you can see cusps, which are due to the higher order approximations that come into play, and these cusp-like aberrations that take place. Apart from that, the intensity is smeared out all over the waveguide region. So one might still go into the non-paraxial region, but the intensity you see is reduced to less than half. So it might not be a good idea to use an extremely non-paraxial input in the case of step index fiber. And I have put self-imaging in quotes because you have loss of perfect self-imaging. That is one thing to notice. The intensity has gone down. The next thing that we notice over here is the distance at which this replication takes place, that is Z, is more than 0.5. If you would have it at the Talbot distance, you would have it exactly at 0.5, but you get it at a distance more than 0.5. The reason for that is quite easy to explain. The reason why it happens is we are considering a dielectric waveguide where the field profile penetrates into the cladding region. So effectively the region over which the field profile is non-zero is slightly more than the width of the code, and therefore the Talbot the width of the waveguide that you would use for the Talbot distance effectively is larger than A, and A is the width of the half width of the waveguide that we had used, and therefore the peak occurs at more than 0.5. Easy to explain that. Now the most important part comes over here, where we have found out the variation of the distance d, or the self-imaging length, with the width of the input beam. And having looked at it, we see that there is a smooth variation, and the self-imaging distance changes by about 15 micrometers from the paraxial to the non-paraxial domain. And in the non-paraxial domain, we find two minimas which occur, and they coincide exactly at the boundaries which were specified by Nemoto. And that led us to the conclusion that the way we have analyzed it is correct, because Nemoto's our calculations are in no way related to the way Nemoto did his calculations for the non-paraxial beam. So if one has to use step index slabs and use the self-imaging point as a point for interconnecting the next element, one has to be careful up to about 15 micrometers, so that a very good interfacing takes place between the slab waveguide and the next optical element. We will now move on. Okay, before we move on to the graded index slab, I'll just talk about comparison of self-imaging in the non-paraxial domain and compare the case of our waveguide with another system, which is the Ronchi grating. The Ronchi grating is a system which has been well studied for the non-paraxial domain, and the expression for the field behind the grating is the one that I have written over here, and these components beta p, they are written as a square root of p, where p is the pth Fourier component in the expansion of the field of the Ronchi grating. So the non-paraxial for the non-paraxial case of the Ronchi grating, you find that this curve in red, which we have plotted for the beta p's of the Ronchi grating, it bends downwards, and the beta p's for the waveguide, they are discrete points, they bend upwards. This black line I have put it for a visual aid, which is a straight line, and in this plot of beta p versus p squared. For the case of a paraxial input, both the red and the blue curves, that is beta p versus p squared for the waveguide and the Ronchi grating, should coincide with the black line, or rather they should become two straight lines. So fundamentally, the non-paraxial behavior of the waveguide and the Ronchi grating, they are quite different. That is the point that I want to make in this plot. And having said that, we for more details, you can look at this article that was published with Dhrubajyoti, a student of IISER. And with that, we move on to the next part of my talk, which is on the graded index slab. How much time do I have? Another 5-10 minutes. Hello, am I audible? Yeah, I have another 5-10 minutes, right? Okay. So I move on to the next part of my talk, where I'll be talking about the graded index slab, and I will be we are going to take a look at this parabolic profile of refractive index, which is the most common graded index profile that one looks at. Apart from the parabolic profile, there are other profiles which have been considered earlier in literature, including the exponential, linear, and hyperbolic profiles, but the parabolic profile remains the most common one. And we use the same formalism, the finite difference scheme, for calculating the modes of the waveguide. And in this case, we will compare it with analytical results. So to do that, if you compare the scalar wave equation with the equation of the quantum harmonic oscillator, you see that there is a parallel, and one can draw the solution, or rather use the solutions of the quantum harmonic oscillator to find out solutions for the scalar wave equation in this case. And the solutions that we can write down, the modes of the parabolic index fiber, we can write it down in this form, which have been borrowed from forms have been borrowed right from the solutions of the quantum harmonic oscillator, and the eigenvalues have been mapped from one system to the other. Rather, we have borrowed the solutions of the quantum harmonic oscillator, and this is the expression for beta m squared. And we have compared these solutions with what we obtained with our finite difference scheme, and they do match remarkably well. I have put error bars for both the second and fourth order schemes, and you find that the second and fourth order schemes yield more or less the same values, no visible difference in them, but there is a slight difference with the analytical values when you go to the higher eigenvalues, the higher order modes. And that the error has been amplified 10 times so that it is visible on the graph. The errors for the lower eigenvalues, which are the ones which you mostly excite in the paraxial or near non-paraxial domain, they are almost negligible. And the field profiles I have plotted on the left, they are the eigenmodes from the analytical expression, and on top of that, you have the field profiles from the finite difference scheme, and one cannot see any visible difference between them. So both the analytical solutions and the finite difference schemes, they are quite well. They tally quite well. And now let's, so for the rest of our analysis, we will be using the analytical form itself. And what we have done here, well, I have rewritten the expressions for the modes, the propagation constants, and some of these variables, which are scale variables of the position x, and this alpha, which is a measure of the numerical aperture that appears in this expression for the eigenmodes. In terms of that, I have written down the eigenmodes and the propagation constants. So if you rewrite the expression for the input, which could be off from the center of this parabolic index fiber, I would write it in this form as long as it is being injected at its waist. And if we calculate the overlap integral of this input with the modes, we arrive at this expression for the coupling coefficients. But this coupling coefficient which is written in terms of these scaled space variable, the numerical aperture, the fundamental mode width. In fact, alpha is also related to the width of the fundamental mode of this waveguide. Alpha happens to be alpha by 2 happens to be the fundamental mode, and sorry, alpha by 2 happens to be 1 by WF squared, and that overlap integral of the input field with the modes of the waveguide will yield these coupling coefficients. But these coupling coefficients are well, this expression holds good as long as the width of the input beam is less than the width of the fundamental mode. Otherwise, this expression Q is going to become imaginary, and it would make no sense to calculate Cm. But if it is completely at the center, injected at the center, x0 would be 0, and it turns out that you can still use the expression for Cm, because the argument for Hm would be 0. Now, what's more interesting is what happens to the intensity as the beam is injected. Well, the beam is injected at z equal to 0, propagates along the waveguide, and it is focused somewhere around 250 microns. And it is focused around 250 microns if the width of the input beam is more than the width of the fundamental mode. And this can be used only if the beam is fed centrally into the waveguide. So this contour plot on the right side is the intensity along the axis of the waveguide. And as I change the width of the input beam, I find that the peak position, that is this position, it shifts. It shows a sudden shift from this line to this line. And we have calculated that, and this is the kind of plot we find. The position of the peak, the position of the self-focusing point, it changes with the width of the input beam. Now, in the non-paraxial and near-nonparaxial domain, we find that the change in this self-focusing distance is comparable to what we had got for the case of the step index fiber and step index slab waveguide. And there is this, and we see there is a sudden change corresponding to this graph. So what happens if you change the width of the waveguide? Just to give you a visual aid, now I change the width of the waveguide to exactly the width of the fundamental mode, and you see that the beam propagates undistorted along the length of the waveguide as expected. Now, when I squeeze the width of the beam even further, the beam expands and refocuses at twice the previous distance. That is over here. So the self-focusing distance has shown a sudden change. And this is something that is expected, known in literature. But the variation of the self-focusing distance in the non-paraxial domain is something that has never been reported so far. If you feed the input along the axis of the waveguide, then one can produce a sudden change in the self-focusing distance. But if there is a misalignment, then you will have oscillations of the beam. So here in these 9 plots, they have been arranged in the following way: the width of the waveguide, the width of the input beam, it changes in each row. So for the first row, it is 0.1 times the fundamental mode. It is 0.4 times the fundamental mode in the second row, and exactly equal to the fundamental mode in the third row. And along the columns, the misalignment changes. The leftmost column corresponds to a perfectly centrally fed input. There's a slight misalignment, about 10 microns for the 62. Well, I should have specified this earlier. The width of the waveguide that we are considering is 62.5 microns. So I've shifted the width of the waveguide, the input beam, by 10 microns from the center in this second column. And in the third column, it is an extreme misalignment where the input is being fed at 18 microns from the center. So it is very close to the edge of the parabolic profile. The edge of the parabolic profile have been marked with the blue lines. Now these are things which one is already familiar with in literature, but if you look very carefully and compare the figures on the extreme left and the extreme right, especially the ones on the first two rows, then you would see that the self-focusing point in the case of this highest misalignment has come down a little compared to what it was in the case of the perfectly centrally fed input. And then we decided to map the self-focusing point, or rather look at how the self-focusing point changes with misalignment and the width of the waveguide. So having done that, we found something very interesting. This is the contour plot of the self-focus, the shift in self-focusing distance with W0 and X0. This is actually W0 by WF. We have not exceeded a value of 1. And we find that there are regions where the self-focusing point goes ahead of the self-focusing point with respect to the perfectly centrally fed case. Those are the regions which are marked in red and slightly above this black curve. So you can see the color bar over here. So extreme misalignment and high and a high width of the input will correspond to the case where the self-imaging distance moves forward, a self-focusing point moves ahead. And if you go to the case of or go closer to the non-paraxial domain, you will find that the self-focusing point actually shifts to smaller distances. And these black curves that you have on this plot, they correspond to those points which do not change, well, for which the self-focusing distance does not change with respect to a perfectly centrally fed input. And that is very interesting. Of all these black curves, the one which is almost horizontal is the one that is most interesting. So we have one width for which the self-focusing distance is not affected by the misalignment. That is more or less the conclusion that one can draw from this figure. But let me also tell you that this is a low resolution plot of W0 in the W0 X0 space. So you could have a lot more structures on this lower left side. That is what is expected. But the most interesting structure is this almost horizontal line in this plot.
Subimal, another 5 minutes left. So can you actually go a little bit faster?
I'm actually done.
Okay.
Yeah, so I'm going to conclude in the next slide. So I have just presented two small works that we have done. One for the step index symmetric slab waveguide, and the other for a parabolic index graded index slab. For the step index waveguide, we have looked at the self-imaging distance, and we have found that it varies by about 15 microns if you change the width of the input from the paraxial to the non-paraxial domain. And the self-focusing distance for the case of the graded index slab, it varies by about 20 microns, which is comparable to the case of the symmetric slab waveguide, only in the non-paraxial and close to non-paraxial domain. For the rest of the domain of paraxiality, or rather For the rest of the domain, you find that it is the self-focusing distance is quite stable and shows a sudden shift as long as you are feeding in the input centrally. And finally, we have also looked at the effect of misalignment. So the misalignment, it shows a change of plus minus 10 microns, of the order of plus minus 10 microns. Actually, it's plus 10 to minus 12 microns. That is the sort of variation that one would see, but it's of the order of 10 microns as with misalignment. So these results, I believe, should be useful if one considers designing nanophotonic circuits with efficient interconnects for optical elements. And for all of these, except for the misalignment part, we have assumed that the Gaussian beam has been fed centrally at its waist. And with that, I would thank the organizers, and I would also acknowledge the Department of Science and Technology, under whose funding I am an RA in the QUEST project. And I would also like to acknowledge Professor Kailash Rastogi for some useful discussions on the problems that we have looked at. Thank you.
Yeah, thank you, Subimal, for a nice talk. And the session is now open for the question and answer. We can actually pick up 1-2 questions from the participants. If you have any question, then you just raise your hand and the organizers will allow you to ask.
Yeah. So I can stop sharing.
Yeah.
I don't think there are many questions.
Yeah, if there is no question, then we can actually wind up this talk and we'll go. Okay, Subimal, thank you once more. Yeah, so let's move to the second talk, and the second talk will be given by the Professor Ashok Vidyagiri from the University of Hyderabad, and